Today we're going to look at convergence of series, and we want to look at infinite geometric sums. Basically, we're going to add all the pieces and see if we can get an infinite sum and see if it converges to a number. So these are our learning targets here today. And if it does converge, then we want to find the sum of that convergent geometric series. First, let's start out thinking about arithmetic series and determine whether we can have an arithmetic infinite sum. So what an infinite sum means is basically you're taking not just a small part like this, but all the numbers off to infinity and adding them together. Let's just look at this arithmetic series here. If I add up this little circled piece here, I get 4 as the sum. That's a partial sum, and that does exist. So we call this a partial arithmetic series. Partial sum, that equals 4. That's for adding 4 terms. Now, as soon as I start to bring other pieces in here, watch what happens. If I add 256 to that, then I get 260. That's certainly larger. And as I add more pieces, notice it's just going to keep getting larger and larger. In fact, it's going to work its way as close as it can to infinity. So for arithmetic series, they will never converge or have an infinite sum. We can only do partial sums. Okay, so let's get into geometric series and see if we can find an infinite sum. So an infinite sum in terms of sigma notation will look like this sigma right here. It'll say 0 to infinity, and it'll give you the rule to the right. This theorem here says that an infinite sum okay, so let's look at this geometric series here. So we have a 2 plus 4 plus 8 plus 16 plus 32. And we want to see if that's going to converge to a number if we add up an infinite number of pieces. So watch what happens. Just like on the arithmetic series, we add up our pieces. This is 6, 14, 30. Right here, this piece is worth 62. And as we add more pieces, you can see our next term in the sequence, or series in this case, would be 64, and then 128, and so forth. This thing keeps going out forever. So how can we determine whether a geometric series has an infinite sum or not? So what we say for this one, we would say this diverges. It does not come up to a single number when we add up all the pieces. So we say a divergent series versus a convergent series. And what we can see here is our ratio is equal to 2. Anytime our ratio is bigger than 1, like this little statement right here, or smaller than -1, because that's what that absolute value means, it does not exist. There's no way we can add it up because there's just too many pieces to add up together. Now, it doesn't mean we can't find partial sums for geometric series. Just like on that last case, I found 62 for the 4 terms that we added together there. We just use this formula for any geometric series. So this formula right here applies to any geometric series that we're working with. So that formula right there. And we've worked with that a little bit in class, where we have A1, N is the number of terms, and R is the ratio. This formula actually reduces down to an easier formula to work with when we have a ratio less than 1 and bigger than -1. So watch what happens. So if we have A1 here, and if our R is a fraction, so something between -1 and 1, when we raise that piece right there to a high exponent, like when I do 1/2 raised to the 100th, I get a really small piece. And if I were to raise 1/2 to the 1000, so as I add more and more terms together, I get an even smaller piece. Okay, and eventually as we go off to infinity, that piece right there, the 1/2 raised to the n, actually goes to 0. So that piece disappears out of the formula. And then we just rewrite the formula. I'll rewrite it down so it's a little bit cleaner here, but it just reduces down to that. Because 1 minus 0, of course, is 1, and 1 times A1 is still A1. So let me clear out here and tell you exactly what formula. Okay, so the piece we want to pull out of this formula, when we have a ratio between -1 and 1, our formula reduces down to this. A1, it's not a very good A there. I'll draw the A a little better. A1 over 1 minus R. That's what it reduces down. Now this only applies when your R value lives between two numbers. Okay, so that means that our ratio has to be a fraction or a decimal in between -1 and 1. So ratios like -1/3 would converge. We say this converges to a sum, as we'll look at some examples here in a minute. Converges to a sum. Okay, some other examples would be the ratio equal to 1/4, or ratio equal to -1/5. Anything that's going to fit into this box right here in terms of ratios, we will get an infinite sum. And that's because each time our pieces get smaller and smaller, as we'll look at an example here in just a second. Okay, here's 3 examples where we're going to just determine whether it converges or diverges. So we'll handle part A here first. First thing we need to do is figure out the ratio. Remember, the ratio is given by the second term divided by the first term. So this ratio is 2/3. That certainly fits into the box where it converges, because each time our pieces will get smaller and smaller. We think about our pieces coming out here. I've got 12, and then the next piece is 6, and then we're going to add 3, and then we're going to add 1.5, and so forth. And notice each time the pieces get smaller and smaller, so it will converge to a number. And we'll look at some specific examples where it converges to a number in a second. Okay, let's look at our second example here. B. So it appears to get smaller here, and in fact that's the case. In this case, our ratio is 2 divided by -4, so our ratio is -1/2. So again, converges to a sum. So we can get one number out when we add all the pieces together. All right, let's look at our third example here. And we're going to say our ratio is given by the second term, 4.5 divided by 3. Okay, and that's going to give us 1.5, which is bigger than 1. So our bigger than 1 or smaller than -1, we say this diverges. We'll never create an infinite sum. We can only do partial sums for that one. Okay, so let's look at a specific example here. We're actually going to find the infinite sum. Okay, so when I look at this series here, it's geometric because it's being divided by 2 or multiplied by 1/2. Okay, so our ratio is 1/2. I got that from 12 divided by 24. Okay, and so it does converge to an infinite sum. So remember, I'm going to use our infinite sum, looks like this, and we're going to say A1 divided by 1 minus r. So in fact, this will be one of the easier formulas you'll use with sequences. A1 divided by 1 minus r. Our A1 is 24. Our ratio is 1/2, so 1 minus 1/2. Okay, so we have 24 divided by 1/2, and that's going to give us 48. So interestingly, if you think about all these pieces laying out there, it adds up to 48 if I take an infinite number of those pieces. It's a pretty neat concept. Again, if we extended our sequence just to see what the pieces do, 24, 12, 6, 3, 1.5, 0.75, and so forth, 0.375. These get smaller and smaller and smaller until they're little bitty pieces you can't even see anymore. They're way out there. And we add them all up, we get 48. An amazing concept there. Infinite sum. Makes you feel smarter. Okay, one more example here we're going to look at for infinite sums. And in this case, it appears that we have fractions for our pieces. So it may be tempting to say this goes to an infinite sum. But let's calculate the ratio real quick. Remember, we do 1/6, second term, divided by the first, 1/12. Okay. So this ratio actually equals 2, and 2 is certainly greater than 1, and so we say this diverges. Because even though these are fractions, and we kind of double these things every time, the next piece we'll get here is 4/3, and so forth. So they get, notice that 4/3 is bigger than 1, and then our next one after that would be 8/3 and 16/3. And we start adding those pieces together, you can see these are bigger than 1, and this sum, okay, will go off to infinity. Great. That concludes our video on infinite series for geometric sequences. Hopefully you enjoyed. Have a great day.